Good morning, everyone. I'd rather be sleeping right now, but here I am. So last time we looked at proving that languages were irregular via fooling sets. The argument made was that in order to capture the described language, if I tried to build a DFA or an NFA for it, I would need an infinite number of states. If I need an infinite number of states, if I need an infinite number of states, I cannot build an automata with a finite number of states. Hence, the language is irregular. So today we'll be looking at a class of languages that is more expressive than regular languages called context-free languages. So I want to introduce some notation very quickly. So if you see something like this, you can treat this black bar, you can treat this as an arrow. These are called production rules. And you can think about this as OR. So what this means is I can start with S, and then I can replace S with either 0S or epsilon. So I can choose to replace S here with the string 0S. Again, I can look at this S and I can choose to replace it with either 0S or epsilon. And I can take this S again and then choose to replace this S with either 0S or epsilon. So let's say I take epsilon and I didn't carry down my 0 from before. So the final string that I get is 0, 0, epsilon, which is just 0, 0. So this context-free language defines the set of all strings, epsilon, or any infinite run of zeros. Can someone give me a regular expression for this language? Zero clean star, right? So for this regular language, I've constructed a context-free grammar. So it turns out that any regular language you can actually build a context-free grammar for, because the class of context-free grammars as a language overall is more expressive and more powerful than just regular languages alone. With that in mind, let's get started with today's lab. So give context-free grammars for each of the following languages. We'll start with this one. So problem number 1. Actually, let's do a quick review. Before we build the grammar, let's quickly prove that this language is irregular. So proof that L1 is irregular. So intuitively, just looking at this language, we see ends, and we want the number of zeros in the prefix to be twice the number of ones, which means that intuitively, if you were thinking about building a finite automata, you would need to keep track of all possibilities of 0-1 pairs, where the number of zeros is twice the number of ones and is a prefix, which makes me think that this language is irregular. In order to prove it, I find a fooling set F. What can I use as a fooling set? 0 to what? 0 to the 2i, and I is the set of integers greater than or equal to 0. And if I take one prefix, 0 to the 2, we'll make this 0 to the 2n, just for clarity. Okay, I take one prefix 0 to the 2i, and I take 0 to the 2j. And what suffix should I put on to make one of them in the language and one of them not in the language? 1 to the I here puts this into the language L1. And if I put 1 to the I here, this is no longer in the language L1. So hence this language is irregular. Because this is irregular, I can't find a regular expression. I can't build a DFA. I can't build an NFA. So I want to construct a context-free grammar for it. So review. So now let's think about using the set of rules that I had before. So we called S, we have some state, or we have some symbol that can produce some recursive definition. where this we say produces or is a production rule, and this is the symbol or, just as a reminder. So let's start here. I want to recursively construct strings where the number of zeros is twice the number of ones. So what's the smallest string in this language? Right, so smallest string is the empty string. What's the next biggest string that's in the language? 001, and then the next biggest one? Okay, so if we look at the pattern here, and if we put the next string in, 0, 0, 0, 0, 0, 0, 1, 1, 1, we start to notice something about these strings. So epsilon I replaced with 0, 0, 1. I kept this 0, 0, 1 here, and then I added 0, 0, 1 to either side. So I took 0, 0, 1 and I put it here. Then I took the next string that was generated, which is this entire string over here, and I added, once again, 0, 0, 1. So intuitively, we can see that we take, if somebody else gave us a string that's already in the language S, so someone else gave us a string already in L1, let's say 0, 0, 1. The smallest thing that I can add on, set of chars I can add on, and to keep the string in the language, is adding 2 zeros to the left and 1 0 to the right. Or sorry, 1 1 to the right. And 1 1 to the right. So if somebody else gave me a string S that's already in the language, in order to keep S in the language, I can add 2 zeros to the left, and I can add 1 1 to the right. I can keep replacing S with this combination, or the smallest string that's in the language is the empty string. Does this make sense to everybody? It's another way of recursively defining strings. Questions about notation, anything? Okay, then I'll move on. Question number 2. The set of all 0 to the m, 1 to the n, where m is not equal to 2n. So we want to build a context-free grammar that is the set of all 0 to the m, 1 to the n, where m is not equal to 2n. Okay, so let's think about this. I want to build something where the number of zeros is not twice the number of ones, and the number of zeros is a prefix. Well, let's try to do a similar approach. What if someone already gave me a string in the language? So someone gave me 0, 1 is in the language, okay? It belongs to L2 because the number of zeros is not twice the number of ones. They're both 1. If I added a single 0 on to the left side, I can't do that because now the string is in the language, right? So if somebody else already gave me 0, 1, and I decided to add 0 to the left side of it, well, now I have 0, 0, 1, m is twice n, and this is not in the language. So this approach won't work. If someone gave me, this is add 0, can I add 2 zeros? So if someone gave me 0, 1, I can add 2 zeros, so that seems to be fine. What if someone gave me the string 0, 1, and I added a 1 on. Seems like that should work. So if we try to build a grammar this way, so someone gave me a string that's already in the language, S, let's just say, and I decide I'm going to add on, every time I add zeros on, I'm going to add 2 zeros to the left in order to break the pattern. Or I can add 1 or as many 1s as I want to the right. I can take S and I can put as many 1s as I want, or I can put the empty string. Does anyone see an issue here? Yeah. Okay, the empty string's not in the language, first of all. There's another trivial issue here. I can take 00S. I can take this S and replace it with S1. And then I get 00S1. Then I can take this S and replace it with epsilon. And then I get 001, which was the exact opposite of what I'm trying to build. So this approach doesn't seem to be working too well. What if we considered it from an alternate perspective? Actually, I'll put this back to. So this doesn't seem to be working too well. What if I first generate strings that follow the format 001 or 0 to the power of 2n comma 1 to the n. So I start by making this string. If I have this string already, this is not in the language. So I start by producing the strings not in the language. In order to put this string into L2, if I add a single 0 to this side, now I'm no longer in L2 because the number of zeros is not twice the number of ones. If I add a 1 to this side, I'm still no longer in L2 because the number of zeros is 2n and the number of ones is n plus 1. So this is not twice the number of zeros is not twice the number of ones. So let's try a different approach by first make all the strings 0 to the power of 2n, 1 to the n. Then add characters to both or either side. To remove the string from L1, which was the previous problem we solved, and place it into L2. Is the approach clear? So we're first building all the strings in this language, and then we're going to add a 0 or 1 to either side to make sure that the new string that we generate is no longer in this language and is actually in this language. So we'll start with the previous grammar that we had, which we'll just call, I don't know, A. And we'll say, in order to produce strings where the number of zeros in the prefix is twice the number of ones, we take 00A or epsilon, right? This is just the previous grammar that we had before. Now, if I have a string that is in L2, or if I have a string of the form 0 to the power of 2n and 1 to the power of 2n, and I do not want it to follow this form, I can add 1 0 or 2 zeros or 3 zeros or an infinite run of zeros before. Agreed? And it'll still not be in the language. So we come back here and we say, okay, I'm going to build a tool that, so this is, to be very clear, this is this language where the number of zeros is twice the number of ones. I'm going to build a tool where I add an infinite number of zeros to the beginning. So let's say we'll call this Z for adding zeros. So I can add an infinite number of Z's to the language. So these are my 0 gets replaced, or 0Z, then this becomes 0Z, and this becomes 0Z, right? So now I have a bunch of different Z's. And I can take this string that I've generated and put it in front of the 0 to the power of the 2n. So I take this infinite run of zeros, or at least one zero, and I place it in front of ZA. So I place it in front of the language A. So I'm starting with this state. From my start state, I'm going to place, I'm first going to generate a string that's 0 to the power of 2n, 1 to the power of n. Then I'm going to place a lot of zeros in front of it to make sure it's not in the language. So what else can I do? I have a string 0 to the power of 2n, 1 to the power of n, that is not in the language. L2. If I want to make sure the number of zeros is not twice the number of ones, what else can I do to modify this? Yeah, add ones to the end. How many? Any number but at least one, right? So I can add one, and now this number is no longer twice the number of ones. I can add 2 ones, I can add 3 ones, 4 ones. I can keep going, right? And then what is a context-free grammar that generates an infinite run of ones? How do I generate at least one one using a context-free grammar? Yeah, W1, right? Or 1, because this will generate at least one, then 2 ones, then 3 ones, then 4 ones, then 5 ones, right? So I take this infinite run of ones, and I place it here. So I take a string of the form 0 to the power of 2n, which is this string, 0 to the power of 2n, and I place at least one, a singular one after it, where we define w to be w1 or 1. Okay, so are we finished? Yeah. Say that one more time. Actually, I screwed this up. This should be a, no, sorry. Give me 1 second. This should be AW, not ZW. Oh, sorry, what was your question? Yes. Do you want this? Because you want at least 1 0. Okay. So let's start testing strings. So let's first test ZA. So ZA puts at least 1 0 first. Z puts at least 1 0 first. A generates strings of the form 0 to the power of 2n, 1 to the power of n. So we're good here. Let's test AW. So we get 0 to the power of 2n, 1 to the power of n. Okay, and then what does W do? W puts 1 or more ones after. So we're good here. Can I generate the string? So we're good here with all even length strings. What about odd length strings? Do I cover odd length strings in this grammar? So someone give me an example of an odd length string that's in this language. Yeah. 0 0, or this is an even length string. Okay, or so you had 0 0. Yeah, yeah. Okay, so this is an odd length string, right? Yeah. So let's actually go. We'll take this logic, but we'll go down to a smaller case. Um, okay, yeah. What's the issue based on this? AW route. Right. Hmm. That's okay. Okay, so add an or replace. So his point was, I think the issue, sorry, was the odd number of zeros, not necessarily. Um, okay, so let's take a string that has an odd number of zeros, and let's look back at this language. So our language was 0 to the power of 2n, 1 to the power of n, where n is an integer greater than or equal to 0. So automatically, if n is an integer and we have 2n, well then this is just the set of even zeros, right? This is 0, 0, 0, 0, 0, 0. So if this number were to be odd by having 1 zeros or 3 zeros, no matter what number of ones I put after it, it's always going to be in the language, right? If this has an odd number of zeros as a prefix, if any string I generate has an odd number of zeros as a prefix, then it cannot belong to the language 0 to the power of 2n, 1 to the power of n. So how do I generate an odd number of zeros? Well, I take an oracle that generates an even number of zeros and add a single zero to it. So production rule A generates strings with an even number of zeros starting. So what if I add a new production rule? Now, this production rule C0A over here, so C leads to 0A. A produces strings of the form 0 to the power of 2n, 1 to the power of n. I add an additional 0 in front, and now 2n plus 1 is always an odd number. So 2n plus 1 is always an odd number, which means that the number of zeros at the start of my string is an odd number, which means I can add any number of ones that I want to the end of it, and the resulting string will still be in the language. So I add on. So I keep 0A, and I start with C, which starts with an odd number of ones, and then I can place any number of ones after it. And what generates any number of ones? My string W. Okay, raise your hand if you're completely lost. Okay, cool. Raise your hand if you're partially lost. Great. We'll go through this again. This is kind of confusing. And if you understand this, like, play Flappy Bird or something. Okay, so I'm going to use the whiteboard. Actually, no, I'll use this. So our goal is to make strings not of the form clear so far. Yeah, so we want to make strings not of this form. So what we do is, first, we make 0 to the power of 2n, 1 to the power of n, and then add zeros to the front. So what does that look like? So I have some 0 to the power of 2n, 1 to the power of n, and then I add a 0 in front. I add a single 0 to the front. Do we now agree that this string is not of this form? Yeah? Okay. If I add 2 zeros to the beginning, do we still agree that this string is not of this form? Yes? No? Okay. So I can add an infinite number of zeros to the front, one or more zeros, and no matter how many zeros I add, the resulting string will never be of this form. The resulting string will be of the form 0 to the power of 2n plus some k, 1 to the n, and k will be at least 1, so it will never ever be of this form. Good so far? Okay. So option number 2 is we first make this string. So we make 0 to the power of 2n, 1 to the power of n, and add on ones at the end. So 0 to the power of 2n, 1 to the power of n, and then I add a single 1 on, right? So this no longer, after doing this, we no longer follow 0 to the power of 2n, 1 to the power of n, right? Because we have an extra 1 here. What is this? This is 0 to the power of 2n, 1 to the power of n plus 1, which is not equal to 0 to the power of 2n, 1 to the power of n. Is that clear? Okay, then we add on 0 to the power of 2n, and if we add on two ones, we get 0 to the power of 2n, 1 to the power of, if we add on two ones, we get 1 to the power of n plus 3, let's just say, right? If we, whatever. We get some constant that we put here, and this number, we'll get some m here, where 2n, we'll get some number here, let's just say 3, where you're never going to have that 2n is twice this number. Good so far? Okay. So let's start building that. So step 1, we build this string. How do we build this? We use the same set of production rules from before. We take two zeros and a 1, and we keep substituting t with 0, 0, 1, 0, 0, 1, or we replace t with epsilon. Does that make sense? Okay. Now, we want to add, option number 1 was, let's add an infinite number, 1 or more zeros to the beginning. So let's make a tool that adds a bunch of zeros to something. So 0. So the smallest string that this can make is 0, or it can make 0z, or 00z, or 0000z. Does that make sense? Okay, great. So now we take this tool z, we could produce an infinite number of 1 or more zeros, and we place it into right in front of the language that generates 0 to the power of 2n, 1 to the power of n, and we obtain a string that's no longer in the language. Does that make sense? Okay. Same thing with ones. So we have, so I said option number 2 is take the string 0 to the power of 2n, 1 to the power of n, and add a bunch of ones afterwards. So we take 0 to the power of 2n, 1 to the power of n, and add ones. So what can we build that adds ones? W gets replaced with W1 or 1. Right? This just generates 1 or more ones afterwards. I take this W and I place it directly after the language 0 to the power of 2n, 1 to the power of n, which is language T. And I place my W right after. Good so far. Okay, last step is, what if my language starts with an odd number of zeros? So if I have an odd number of zeros, so let's go back conceptually here. If I start with odd number of zeros, so let's say I take 0, 1, or 0, 0, 0, 1, or 0, 0, 0, 0, 0, 1, 1, 1, 1. So if I start with an odd number of zeros, we do not want strings that take the form 0 to the power of 2n, 1 to the power of n, right? If the number of zeros in my string is odd, I will never have 0 to the power of 2n at the beginning, because 2 times an integer is always an even number. So if number of zeros is odd, I will never have 0 to the power of 2n, because 2n is even. Following still? Yeah? Okay. So what do? I take 0 to the power of 2. I make something that starts with an odd number of zeros. So I take an odd number of zeros. Let's say 0, 0, 0, 0, 0, 0, 0, 0, 0. And then I can add on as many ones as I want. And no matter what string I produce that starts with an odd number of zeros, it will never have the format 0 to the power of 2n, which means it'll always be in the language. So let's modify this to make a new production rule. Let's call it, let's just say D for now. Let's take a string that has an even run of zeros and replace it with a string that has an odd run of zeros by putting a single 0 in front. So now D makes odd numbers of zeros at the beginning. So I have 0, 0, 0, 0, 0, 0, 0, 0, 0, and I can put as many ones as I want after. So we take odd number of zeros, D, and then I can put as many ones as I want after it, which is the language W. I defined W somewhere, but I didn't move it up. Does this make more sense than it made before? Yeah? Okay, let's move on for the sake of time. So which language does the following pushdown automata recognize? This is a non-deterministic automata, as most PDAs are. So you can think of a pushdown automata. Let's start here. Regular languages, languages accepted by DFAs and languages accepted by NFAs are the same. Context-free grammars, grammars that can be written by a set of production rules that I've described above, and languages accepted by pushdown automata are the same. So context-free grammars pushdown automata accept context-free grammars. So we're going to define some notation here. We have a bunch of states which look similar to our NFA, DFA states. We have epsilon transitions that look like our NFA, and the only thing that's different is what we put on the arrows here. You can think of a pushdown automata as an NFA but with a stack. So, idea. So let's pick an arbitrary transition symbol here. So let's take this transition symbol here, B comma A arrow epsilon. So we have this transition symbol. What does this mean? So we have some input string, B, B, A, C, let's just say. This means read B from the input string. So that crosses this B off. This means pop A off of the stack. So if my stack state had, let's just say the character A, what it would do is it would pop A off of the stack. And this means push epsilon, which is the empty string, onto the stack. So that's kind of what these production rules mean. And if you want to generalize this, you can think about this as just this is the character that you're reading, comma, what you are going to pop off the stack, arrow, what you're going to push onto the stack. Does everyone understand the notation of the transition function? This means you read epsilon, you pop a $sign off of the stack, and you push epsilon onto the stack. Does that make sense? Okay. So the question says, what language does the following pushdown automata accept? So let's start with strings. What do we see here? Let's pick the string. So we have the character A, we have the character B, we have the character C. So let's just test the string ABC and see if the pushdown automata accepts the string. So what happens? We have our start state here. There's only one transition option. This means we have our string ABC. This means read epsilon from the string. So I have my stack. This means pop nothing off of the stack and then push a dollar sign onto this stack. Now we're in this state. So we have two options from the state, just like an NFA. We can go to this execution path. We can go through this execution path. Actually, we have three options, or we can go through this execution path. Just like an NFA can have many, many transition or execution paths for the same string. If one of the paths in an NFA leads to an accepting string, then you say that the NFA accepts the string. Similarly, in a pushdown automata, if one of the paths leads to an accepting state out of all of the possible paths, you say that the PDA accepts the string. So let's try path 1 first. We'll call this path 1. So what does this say? This says read nothing from the input string. So we haven't read anything yet. Pop nothing off of the stack and push nothing onto the stack. Great. Now we're in this state. What does this state say? So again, we haven't consumed a single character of our input string. This says read B from the input string. Well, shit, I don't have a B here. So we're stuck. We can't go anywhere from path 1. Does that make sense? So this says read a B. I haven't gotten to a B yet, so we know that path 1 won't accept the string. So let's cross that out. That goes away. So let's go back to this state. Actually, we'll try path 2 now. So we haven't read a single character. This says read nothing from the string, pop nothing off of the stack, and push nothing onto the stack. Okay, that's fine. We move on to state Q5. What does this say? This says read a B from the input string. Again, I have no B, so I can't do anything. So this path doesn't lead to an accepting state. So the only path that I haven't tried is this path. This is path 3. So what does this say? This says read A from the input string. So now I've read A. Pop nothing off of the stack. So I'm not popping anything off. And push A onto the stack. So now A is on the stack. Once I'm in Q2, I have only one other option, which means read nothing from the stack, read nothing from the input string, pop nothing off of the stack, push nothing onto the stack. I now come here. This says consume a B from my input string. Let me consume this. Pop nothing off of the stack, push nothing onto the stack. Great. I take an epsilon transition that doesn't modify the stack or read any input characters. What does this say? This says read a C from the input. So I've read the C from the input. Pop an A off of the stack. I pop A off of the stack and push epsilon or push nothing onto the stack. So I'm not pushing anything onto the stack. This is now gone. Finally, what does this say? Read nothing from the input. Pop the dollar sign off of the stack. So I pop this dollar sign off. And push nothing onto the stack. And now I'm in an accepting state. So my stack is empty, and I'm in an accepting state. Does this make sense? So all you're doing is you're taking a string, you're simulating the given string on all possible execution paths of the PDA. If one of the execution paths leads to an accepting state, then we say that the PDA accepts the string. If none of the paths lead to an accepting state, we say it rejects the string. Notice here the purpose of the dollar sign. So in our start state, the first thing that we do is we read nothing, we pop nothing, and we push a dollar sign on. In the last state that we have, we read nothing, we pop the dollar sign off, and we push nothing. By design, the reason for this is that the only way this PDA can accept a string is if the stack is empty by the time you're done executing it. This dollar sign serves as a control mechanism, and it's not part of the alphabet sigma. And the purpose of it is to make sure that by the time you reach an accepting state, your stack is empty and you're in an accepting state. So we know that ABC works. So ABC is in the language, is in L. So let's experiment with a few more strings. So let's take this path of execution. I read nothing. This consumes all of my A's. This consumes all of my B's. And then, so I need to read nothing. I need to, I read all of my A's and I push all of my A's onto the stack. That's what this does. This reads all of the B's, so we can write that down. This reads all A's and then pushes all A's onto stack. This reads all B's and pushes and pops nothing. Okay. And then what does this do? This reads all C's and pops all A's. And then just pops the $sign. So what do we notice here? Exactly, right? So this reads all the A's and pushes them onto the stack. This just consumes all of the B's and does nothing with them and throws them onto the floor. This reads all of the C's and pops all of the A's off of the stack. So the only way for the stack to be empty is if the number of A's and C's are equal. So we notice one path of execution. So number of A's needs to equal number of C's. So that's option one. Option number two is, let's go through the other path now. So what does this do? We already said this reads all of the A's, pops nothing off of the stack, and pushes A onto the stack, correct? So this pushes all of the A's onto the stack. We do nothing, and then we get here. What does this state do? This state reads all of the B's that I have, pops all of the A's off of the stack, and pushes nothing onto the stack. So again, this pushes all my A's onto the stack. This reads my B's and pops all of the A's onto the stack. And then I epsilon transition into an except state. So what does that mean? This path of execution cares only if the number of A's is equal to the number of B's. So this path and then what happens when you hit a C? Well, you push nothing and pop nothing. So the path on top only cares if the number of A's is equal to the number of B's and doesn't give a shit about the number of C's. The path on the bottom only cares that the number of A's is equal to the number of C's and doesn't care about the number of B's. However, in both scenarios, the B's need to be sandwiched between the A and C if they're consumed. So we have a language of this form, A to the X, B to the Y, C to the Z, where either the number of, where either X, the number of A's is equal to the number of C's, so X equals Z, or Y equals, or the number of, Jesus Christ. X equals Y, thank you. The number of A's is equal to the number of C's. Does that make sense? So let's test the string DC. So by definition, we said, as he said, in order for a PDA to accept a string, out of one of all of the execution paths, you need to consume the entire string, you need to be in an accepting state, and the stack needs to be empty, right? The stack does not need, well, the way this PDA is designed, the stack will be empty if you accept. So let's test the string BC. In BC, does the number of A's equal to the number of C's? No. Does the number of A's equal to the number of Y's? No. So BC is not in the language. So great, we have the definition right now. Okay. So I think this is the language, unless there are any objections. It's good that this BC thing is consistent with the definition.